All right, welcome students to this video. This is Pre-Calculus 20 review video, and this is a video you can watch while studying for your final. I've attempted to put the whole course into one video, so we're going to go through this pretty quick. I'm not going to teach too much on it. I'm just going to do a little bit of a refresher. So hopefully this is going to be Pre-Calculus 20 in 20. So I'm going to start the timer right now, and I'm hoping we're going to do this in 20 minutes. If you want to watch it in fast speed, 1.5 or 1.75 times, it might help. If you know what you're doing and you just want a refresher, put it on high speed, and you can get the whole course in a fraction of the time. So here we go, all the way back from 1.1. So we're starting with series and sequences. Now a sequence is a list of elements or a list of numbers, and there are aspects of a sequence that we can look at and put into a formula. So you might remember this formula, the T of n formula. T of n equals T of 1 plus n minus 1 times d. Now this is a formula dictating all of the numbers in a sequence. So for example, T1 is the first term, and here T1 is 2. It's the first term that's listed. N is the number of terms in the sequence. So in this one, 1, 2, 3, 4, 5, we have 5 terms. The D now is the difference, okay? It's the difference between the terms. And when we have a special sequence called an arithmetic sequence, the difference between each term is exactly the same. And here we see that D is positive 3 because the numbers increase by 3 each time. Now, T of 3, that is the third term, okay? T of 3 means the third term. It's not the number 3, it's the third term. So here's the first, here's the second, and here 8 is the third. So T of 3 is 8. If I use this formula and put 3 in for n, and put my D there and put my T1 there, I will actually get the value of 8. And I'll let you try that out on your own if you want. So that's 1.1. 1.2, we talked about a formula for an arithmetic series. Now what's the difference between a sequence and a series? Well, a series is the sum of all of the terms in a sequence. It's the sum. So here, this big S right here, this is the sum of the first n terms. And if it's an arithmetic sequence like we just talked about, here's a formula for finding the sum of the first n terms. So for example, 2, 4, 6, 8, the sum of the first 4 terms there would be the number of terms, that's 4 over 2, times the first term plus the last term. Now this one, you have to know the last term in order to use this formula, Formula 1. If you don't know the last term, if you don't know what the value of that is, you can use this one, Formula 2. You still need to know n, you need to know the first term, but you notice you do not need to know the last term. And really, we're just substituting this a bit here in for T of n, which we learned in 1.1. Moving to 1.3, we're talking about now geometric sequences, okay? Geometric sequences are, again, a list of numbers, but instead of being separated by a common difference, they're separated by a common ratio. That would mean like if you had something like 1 and 3 and 9 and 27 and so on, this would have a common ratio because each term in the sequence you would multiply by 3 to get the next term. So that common ratio is the R. Now this looks a little bit confusing maybe. T of n equals T of 1, that's the first term, times the ratio to the power of n minus 1. So in order to get 27, I take 1 and I multiply it by 3 to the power of, how many are there? There's 4 terms, so that's 3 to the power of 3. First term times 27 equals 27. All right, so that is your geometric sequence formula. All right, how am I doing? I got 14.5 minutes left. Wonderful. Okay, moving on to 1.4. Again, we've talked about geometric sequences. Now we're talking about geometric series. Again, that is the sum of all of the terms in a geometric sequence. So if we had something like 3, 6, 12, 24, you know that the common ratio there is 2, right? Because we're multiplying by 2 to get each term there. And it's a series, that means we have to add them all up, okay? And that's all it is. You just add up the terms in the sequence. And I'm going to have some formulas here for you for geometric. I'm going to have some formulas at the end. And here they are, the sum of the geometric right here. So this is the geometric. Here's arithmetic right here, these formulas right here. And this is the sum formulas, excuse me, for geometric terms. And we'll get into this funny one here in a minute. But those are the formulas you can use for a certain number of terms. Again, if you know the last term, that's great. If you don't know the last term, well, then you can use other ones. So that's 1.4, talking about geometric series. 1.5, we talked about convergent series, divergent series, or the sum of what we call an infinite geometric series. Now this has far-reaching applications in calculus and so on. We won't get into that in this course, but what you need to know is that this little infinity sign here, right, and the s with the infinity sign as a subscript means that we're taking the sum of an infinite number of terms. So look down here, here's an example, 2, 4, 8, 16, those are the terms, and we're adding them all up, but you see these little dots right there? That means that we're adding up all of the terms in the sequence up until the number of terms approaches infinity. Now a divergent series we cannot find the sum for. Why? Because we're always going to be adding another number that's really, really huge, and we're not going to center in on a specific sum. It's only when we have a convergent series that we can actually find the sum. So this is really important, the sum of the infinite number of terms of a convergent series. So this formula is actually really easy because you take the first term and you divide it by 1 minus r, the common ratio. And again, we can only find the sum for convergent series, right? So that, look, at these are getting closer and closer to 0. The r is between -1 and 1, like it's less than 0, it's a fraction. So that means these numbers are getting smaller. So you can imagine at the very end, we're basically adding something that's like 0, so we can come to a determination of what the sum actually is. Over here, we're adding a billion, then another billion, and then another, like it's not zeroing in on anything. So again, here are your formulas for chapter 1. You might want to pause, and you might want to write these down, on a study sheet or something. But again, I will comment on this one right here. The sum for geometric is right here. Look, it's got a ratio. That means it's geometric series. And when you know the number of terms, you can use this one. This one over here you can use when you don't know the number of terms. You know the first one, and then you have you know what the last term is, I guess, or the term you want to add. Yeah, the last term right here. So number of terms, last term. So here's the formulas for chapter 1. All right, it moves us to chapter 2. We're talking about angles, we're talking about quadrants, and we're talking about theta. I think we talk about maybe radians, or maybe not radians in this course actually. But let's see, 2.1. So if we're talking about an angle in standard position, the initial arm right here is on the x-axis, and it's extending from the origin, where the vertex is there, to the positive way. So this is a standard position angle. The quadrants are labeled 1, 2, 3, and then 4, and that's going to come in handy when we describe where the terminal arm is for a whole bunch of angles. And okay, so that's that initial. Yep, good. All right, what's a reference angle? Well, if we have an angle that specifically for ones that are greater than 90, it's often going to be very helpful for us later to know what the reference angle is. And the reference angle is the angle, the acute angle between the terminal arm of an angle right here and the nearest x-axis. So it's the acute angle that's formed from the terminal arm and the x-axis. And there's a special relationship between the reference angle and the actual full angle. Okay, there's a very special relationship which we're going to talk about a little bit later. The other thing you want to memorize is your special triangles. Here's the 45, 45, 90 triangle, and here is the 30, 60, 90 triangle. These are very important when we're talking about trigonometric functions, which we're going to get into here soon. So those are the special triangles that will be referenced later. All right, 2.2. Here's where we start to talk about trigonometric ratios, okay? And you've heard about trigonometric ratios before, ever since you were a little bitty baby, right? You've heard about sine, cosine, and tangent. And you know that for a triangle, okay, and if this is the angle right here, that the sine is the opposite over hypotenuse. That's so, right? Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, so katoa. Well, now when we're dealing with the coordinate plane, when we're talking about x and y coordinates for a point, this side of the triangle is x, this side is y, and the hypotenuse is actually r. It's the distance from the point to the origin. And so now we have a new memory mnemonic, which sounds kind of funny, I know, but it's called Sir-Coxer-Tix. Sir-Coxer-Tix. And that's s equals y over r, and that's really the same as opposite over hypotenuse. And then cosine of the angle is x over r, and tan is y over x. So we're talking about trigonometric ratios now, and all we need is a point. All we need is a point in the coordinate plane, and we know what x is, we know what y is. We can calculate really quickly what r is, the distance from the point to the origin, or you can use Pythagorean theorem, right, to calculate r. A, B, this is C. So a squared plus b squared equals c squared. You can calculate all of the, and of course that's a 90-degree angle there. All right, so here are the key ideas there. The other thing I want to note, make mention to you is this quadrantal angles. Those are the angles that end up on the x and y axes, the terminal arms. So like 90 is a quadrantal, right? It's not in quadrant 1. Here's quadrant 1. It's not there. It's not over here. It's exactly right on the axis. So those are called quadrantal angles. Now, the other thing too that I don't know if it's mentioned here in this section, but you're going to need to know, and you should know this already, but this is called the cast rule. Okay, and what this does is it helps you determine, and we'll focus maybe more on this a little bit later, but it helps you determine which trig functions are positive in which quadrants. So if I have an angle that ends up in quadrant number 4 right here, okay, let's say I'm talking about this big angle, I know that cosine of that angle is positive. Tan and sine are negative. So whatever letter is here, that's what's positive. Cosine here, tan here, sine over here, and all are positive in quadrant 1. Okay? So that's the cast rule, a little bit on that. 2.3, we talked about the sine law. Okay? So the sine law is when we're talking about triangles that aren't necessarily right triangles. We have an angle A, B, and then an angle C. We have a little a is the side opposite of angle A. Here's little b, here's little c. So for a triangle like this, the sine law states that you can take the ratio of any side length and its opposite angle, as long as you use the sine of that angle, and you can put it in a ratio. You can take any two like this, and you can make them equal. You can, of course, do these two as well, or this one and this one. You can make any two equal. That means if you have 3 pieces of this, you can solve for the 4th one. Okay? It's a over sine A equals b over sine b equals c over sine b, or you can flip them all around, and that works as well too. That's the sine law. The tough part about this section, I think, was the ambiguous case. If you remember the ambiguous case, and that is if you are given that you have certain certain parts of a triangle, you have a certain angle here, you have this side here, and then you have the following side here, you are asked to determine whether this actually forms a triangle or not. It's a little ambiguous, it's a little mysterious. You don't know if there's 0 triangles, which would be this case, where A is not long enough to actually reach the base here. Or you could have a case where you have exactly one triangle where this A length is exactly the right length to form a right triangle here, in which case the sine of theta would be A over B. Okay? Or you could have more than one triangle if this A is actually a little bit longer than the minimum necessary to form a right triangle. And the triangles might look like this. There's your B, there's your angle, and here is your A. So this triangle right here. Or this one right here, where you have this B, you have this angle, and then you have this long A over here. So A could be there, or A could be there, and you have one triangle, 2 triangles. That's the ambiguous case. How I like to teach this is you can always check what the height is by taking B and multiplying by sine of A. That will give you always H, because it's a right triangle. You would compare this length of H with the given A. If A is less than H, you have no triangle. See, it's too short to make a triangle. If if H is equal to A, then you have one triangle, like I showed you over here. And if A is greater than H but less than B, you have 2 triangles. Now what happens if A is super long and it's bigger than even B? Okay, so this doesn't end here. This A is super long and it's even longer than B. Well, then you have this really long triangle like this, and it's shorter than this one, and you just have one triangle. If A is greater than B, you have one triangle. That's the ambiguous case. I would encourage you to look at the full lesson there, and that's in section 2.3, and you can look that up on my channel if you want the full lesson. 2.4, we talked about the cosine law. Now the cosine law also uses a trig function, the cosine right here, but in cases where you have every side of a triangle listed but you don't have any angles, that's the side, side, side situation, or where you have a side and another side and the angle in between those two, that's a side angle side situation. These are good candidates for the cosine law. You can solve for opposite side, you can solve then for these 2 angles. Here you can find an angle, then you can find another angle, and then find the third 180 minus those 2. So that's the cosine law, and it's in the pattern of this right here, this pattern right here, where you have the length of one side opposite of the angle that's going to be used in this formula. That's cos C over here. So C and then cos C over here. And again, you can take a look at this. The cosine law is used in these situations. Look up the full lesson if you need it. And that's chapter 2. So let's move on to chapter 3. How are we doing? You guys with me here so far? Okay. Chapter 3. Chapter 3, we start talking about quadratic functions. A huge part of this whole course, right? Quadratic functions. They are in the shape of a parabola. Here's a parabola right here. That's this sort of almost like kind of up cup, down frown sort of shape. That's what a quadratic function makes. A quadratic function has an x squared in it. F of x equals some kind of x squared. That's how you get a parabola shape. If it doesn't have an x squared, if it has x cubed, not a parabola, and not a quadratic. If it has just an x and no x squared, it's a straight line. It's not a quadratic. Okay. So if the parabola opens upward, you would have the vertex down here would be a minimum. Okay. If the parabola opens downward, the vertex up here would be a maximum value. Okay, so that's where min and max comes from. If it opens upward, open downward. Now, how do you know if it opens upwards or opens downwards? Well, the vertex form of a quadratic looks like this. This should be familiar to you. What you want to know about this is the a value dictates whether it opens up or down. If a is greater than 0, that means it's positive, it opens up. Okay, if a is less than 0, that means a is negative over here, it opens downward. Very, very important. If a is a large number, like let's say it's 10, that means this parabola opens very narrowly. It's a very narrow opening, either up or down, okay, positive or negative 10, let's say. And I'll show you a little bit later, or maybe I'll show it to you right now. Okay, if we look down here at this diagram right here, what I like to remember is that if you can always guesstimate what the a value is by looking at the parabola, and this is not taught very often, but if you go from the vertex and if you go over 1 unit, and then however many units it takes you to go up to get to the parabola, or however many units after you go over 1 it takes to go down to actually land on the parabola, this is the a value right here. That's the a value. This is a value. So you can guesstimate, and I guesstimate that this is about 1.5. See, 1.5 units. So that's a good thing to remember. Okay, if it's a is really large, then that means it takes you a long time to get up to the function, and it's narrower. Okay. I guess, let's see, was I done with everything over here? Vertex, okay, parabola, minimum, good. Okay, so here, this talks about, right here, you can freeze this screen and study this if you want, but the vertex is at PQ for this form right here, okay? So here's the vertex form right there, and the P value and the Q value, that's the X and the Y coordinates for the vertex, okay? Vertex is the minimum or the maximum, depending on which way it opens up, vertex. That's the coordinates. And A is the width of opening and the direction of opening. So you can read through that. That should be just a review for you. There's a bunch of examples. You can take a look at that. And yeah, so that's that page. That's 3.1. 3.2 talks about the standard form now of a quadratic, standard form. Now, the standard form looks something like this, okay? F of x is ax squared plus bx plus c. This is the vertex form right here. This is the standard form, okay? They're different. All right, same parabola, mind you, same parabola, they just look different. This one shows you what the vertex is and clearly what the a is. This one does not show the vertex clearly, but it does still show the a right here, okay? It's attached to the x squared. Now, how do you get from vertex form to standard form is really easy. All you do is you expand, and notice how this right here, I just did FOIL, x minus 3 times x minus 3 to give me this. Expand that 2 into each term, and then combine and gather like terms like these two, and you get your final, there you go. All you do, expand, gather like terms. That's how you move from vertex to standard form, okay? Here's also a helpful hint, and again, if you're writing this down in your study notes, you might want to write this down so you can look at this later. The axis of symmetry, oh my goodness, that means I only have 2 minutes left to do this under 20. I am totally, that's not good. Okay, I'm going way slower than I thought it was. I apologize. So this is going to be a little longer video than I thought. Anyways, whatever. Okay, where was I now? Where was I? Oh yeah, axis of symmetry. Let's go back up here. The axis of, wow, nice guess, Maxwell. The axis of symmetry is the vertical axis that splits a parabola exactly in half, and it runs through the vertex. So the x value of the vertex is going to be the equation of the axis of symmetry, and you can find that from the standard form by plugging in b, which is this one right here, divided by 2 times a, and then taking the negative of that. So here's an example for this one. Negative b over 2a gives us 3, and that is, as we saw in the vertex form, that is the x value of the vertex. Okay, this is plus 3 is the x value of the vertex. It's always the opposite sign of what you see here. So x equals 3 is the equation of the axis of symmetry. All right, 3.3. So 3.3, we are completing the square. This is how you go from standard back to vertex form. Okay, this is a bit tough. You're going to want to watch this full lesson if you're not remembering how to complete the square. But here's the key to completing the square. You want to look at the b value right here. That is the ticket. If this is a 1, all you do is look at the b value and you go b divided by 2. Okay, that would be -4, and then you square it. What does that do? Well, that gives you the number that goes right here in order to make this plus this term plus this. That makes it now a perfect square trinomial. Okay, take half of this, square it. This makes this a perfect square trinomial. And why is that important? Well, if you can write this perfect square trinomial as a binomial all squared. Wow, that's what we have in the vertex form. So this is how we now do this. Now, what about this part over here? Well, remember, you can't just go ahead and add a value to one side of an equation and call it the same as it was before. So if I'm adding something in here to make this a perfect square, I have to subtract something outside of these brackets, or I have to add the same thing to the other side, which is in effect the same thing. So here you go, b over 2 squared goes there to make this a perfect square trinomial, but you also have to subtract this so that this balances it out, so you're not actually changing the equation. You're just rearranging things to change the form. And completing the square is how you go from standard form to vertex form. And that's chapter 3. Chapter 4, moving on real quickly. Chapter 4 is talking about quadratics and solving. So now we're looking at quadratic equations, okay? A quadratic equation, right here, is where I have some kind of quadratic function, okay, as an equation. So I have an equal sign there. Equals, it can be equals anything, all right? In the case where it equals 0 is a special case where we can really solve this really easily. And one of the ways you can do this is graphically. What do I mean by that? Well, if you take a look at this function right here, okay, y equals f of x, if you just, f of x right here, if you just put a y in front of it, y equals, and you pretend this is a graph right here, then you can graph it and you'll graph this parabola. Now, how does that help you? Well, if you have a 0 on this side, which is really important, then the intercepts of the x-intercepts for this parabola, those are the x values that cause this left side to equal 0. Well, that's handy. Those are the exact solutions we're looking for. So, if you have an equation where you have some kind of anything, polynomial, quadratic in this case, and it equals 0, plot the corresponding function and find the x-intercepts. And right here, -3, 0 is the x-intercept, 2, 0 is the x-intercept. -3 is a solution to this equation, and +2 is a solution to this equation. Okay? So the roots and the zeros of the corresponding quadratic function are the solutions to the quadratic equation where it equals 0. Make sense? Y is 0, that is the x-axis. So where are the points where the graph crosses the x-axis? Okay, 4.2, solving quadratics algebraically. We use something called the zero product principle, and what you do is you take the, right here, and I'll just move this down so you can see all of it at once. We're going to take the quadratic equation here, this equals 0. What we're going to do is we're going to factor it. Check for a greatest common factor, pull that out first, focus then on the trinomial, and factor it into 2 binomials if you can. Once you do that, if you're able to factor it like this, great, you can use the zero product principle. And what I mean by that is this, is that this left side is 0 when one or more of the factors also equal 0. So if this is 0, you have 2 times 0 times anything, and it's going to make this side 0. If this is 0, you have 2 times something times 0, it's going to make it 0. So let's test and see what x value makes each factor 0. In this case, -3/2 makes this 0. In this case, +2 makes this one 0. So those are your 2 possible solutions. So factor out the greatest common factor, factor the trinomial, let each factor equal 0, solve for x, verify. So verify means you want to plug this value into the original equation, make sure it's true. Plug this one in, make sure it's true. In the case where you have a word problem or something, you algebraically may get 2 possible solutions, but one may not be possible. You might have to reject it. For example, if this represents some kind of length, and you get a negative value for a length, you have to reject that. You take the positive one. That's an example where you might have to reject a possible solution. All right, take a drink here, Jeff. All right. 4.4. All right, 4.4, what does it talk about? It talks about the quadratic formula. Here's another way to solve a quadratic equation. You want to find the roots? No problem. You can plug in the a, the b, and the c value from your standard form. There's a, there's b, there's c, the coefficients and the constant. And you can plug it into what's called the quadratic formula. Now, I have a song about the quadratic formula. There's a whole lesson. It's very important. Go look that up if you want. Here's the quadratic formula. Again, what this does is it solves for roots or intercepts of a quadratic function. And of course, if you have some quadratic equaling 0, you can use this to find your solutions to this equation. The discriminant here is a piece. It's just a part of this quadratic formula. And this is a big indicator as to whether you'll have 1 root, 2 roots, or no roots. So in this case, this function right here clearly does not touch the x-axis. That means there are no roots. Well, what would that look like? If you just plugged in b and then a and c in here, this would be a negative value. In this case, the discriminant would be negative. You can't take the square root of a negative to find a root. So there are no real roots, which means that there are no roots. There's no x-intercepts. Okay, if the discriminant was 0, you would have exactly 1 intercept, okay, like this. And if b squared minus 4ac is greater than 0, it's positive, then you know you have 2 discrete, distinct intercepts like that, okay? So that's 4.4, the quadratic formula. All right, looks like we're moving on here. Let's get to chapter 5. Whoa, 7, oh, 7, not yet. Okay, chapter 5, we're talking about functions and equations again. Let's talk about radicals. Okay, radicals are these things like this, 5 root 7 or negative root 7 cubed root of 5x squared. Wherever you have like a square root or a cube root or that little root sign, that's a radical. And we can work with radicals. There's a few important things we need to notice though. Like radicals, have the exact same index, or that is a square root. They're both the same types of roots, and they both have the exact same thing underneath the root signs. These are like radicals, and we can combine the coefficients in front into one radical. So this would be 5 and a negative 1. So that would be a 4 root 7 if we were to add these together. Unlike radicals, have different radicands, the numbers underneath the radicals, or they have something like the different index. So that's a 4th root, this is a 5th root. Those are unlike. Some things that we need to know about radicals is that if you have a radical with an even index, that is 2, 4, 6, 8, etc., you cannot have a negative value underneath here. So 4 minus x, you can actually evaluate this. This is a real answer for this, but only when 4 minus x, is 0 or positive. And so that's why you can take this, what's called radicand, and you let it be equal to or greater than 0 and solve for x. So this is your restriction on x. If x is anything less than 4, x has to be less than 4. Yeah. If x is greater than 4, then this becomes a negative value, and that's no good. Converting mixed radicals to entire radicals is another important part of this course. And again, if you have this is called a mixed radical because it's got a real an integer part and a radical part. And so the 7, to get into this radical here, has to get whatever this is. This is a 2, a square root. It has to get squared. Then it can come in as a factor. So that 7 becomes a 7 squared inside there, and this is your entire radical. That means the entire number is underneath the root sign. There's no whole number part out there other than 1. Same thing here. This is an a, and this is this is a to the 4th, and that's a square root. So you got to square that, and then it can be a factor underneath there. Multiply them, you got your answer. Going the other way is a little bit different, a little bit trickier. What you need to do is you need to take a look at, do I have any factors of this number that are perfect squares? That's what I always look for. And then you can separate this as root 2 times root 100. So that's a property of radicals. And root 100 can be simplified, and so you now have 10 times root 2, and that is how you change an entire radical to a mixed radical. That's a little bit different for variables. If this is a 4th root, you have to try and find out the c to the power of what that is, multiplied by itself 4 times to get this. The simple way to find that out is do this exponent divided by 4, and that's going to be your 4th root. So here, if I have a 9 here, I need to split that into c with a even value that I can divide by 4, or a divisible by 4, and then I can simplify that to c squared. So c squared is the 4th root of c8. If you can't simplify, you have to leave that piece underneath there, and that's your answer. So I'll let you just take a quick look at that for 5.1. 5.2 is called rationalizing the denominator. Now, if we need to get rid of a radical in the denominator and we have some kind of binomial there, what you do is you multiply it by the conjugate. The conjugate is the exact same first and second term with the opposite sign. And what you do to the bottom, you have to do to the top, because we don't want to change this rational at all. We just want to change how it looks. So when you multiply the top and the bottom by the conjugate of the binomial containing the radical, you get something that looks like this. Now, we do have radicals in the numerator, but all we want to do is rationalize the denominator, and that's going to be helpful for a lot of applications moving forward in math. Okay, so that's rationalizing the denominator. Remember what a conjugate is. Multiply top and bottom. All right, if we have a radical equation, again, what we're looking for, an equation means solve for the unknown part. So I need to find out what x is, but I need to get it out of this root sign, okay? It's tough to get this isolated by itself with this root sign. So what you do is you take everything but the radical part over to the other side of the equation, and then you square both sides. Now, if you square a square root, you know that that's an opposite operation. So squaring a square root is going to get rid of the root sign, okay? One thing you have to notice is that if you have square root of anything and you have a negative number over here, that's bad, okay? That's bad. You can't do that. There's no value, there's no answer there if you run into that. So just remember that one. Okay, I'll move that down so you can see that. But if you square both sides and get rid of the radical part, then you just treat this like a regular equation and solve for your x. Now please make sure you check, because when you do stuff like this, when you square both sides, that you get into some trouble with the math a little bit, and sometimes you can get an answer that doesn't actually fit in your original equation. So you have to check every time. In this case, I did plug in my answer, and this statement is true. The original statement does turn out to be true, so this is my acceptable answer here, x equals 25. That's 5.3. That's the end of Chapter 5. Chapter 6, we're talking about rational expressions in equations. So a rational expression is anything where you have like a ratio. See that? It's a ratio. Here's a ratio of two terms. And usually one or both of them are polynomials like this, and that's where we kind of have to work with this kind of stuff. So the non-permissible values would be any x values that make the denominator equal 0. Because remember, you can't divide by 0. That's no good. That's no good. So non-permissible values would be anything that makes the denominator 0. So if we want to simplify a rational expression, here are some steps that we need to follow. First of all, we want to factor the numerator and the denominator like I did up here and down here. You want to factor them. Why is that? Because you're going to want to simplify by dividing out any common factors. Before you move any further, though, after this, is you want to note your restrictions. So take a look at what you have in the denominator. Set each of these equal to 0, like this, and then you'll find here that x cannot equal negative 5 over 2 when you solve this, and x cannot equal positive 2, because that would make these factors 0. So the second step is noting your restrictions. Then what you do is you divide out common terms like I have here and write whatever's left over. This is your final answer. That's simplifying rational expressions. Make sure you include your restrictions in there as well. Make sure you circle your answers. 6.2, multiplying and dividing fractions. When you multiply and divide fractions, you know that you can just multiply straight across, right? Multiply straight across. Well, it's going to become pretty onerous here to actually multiply these things out. So what we want to do is we want to simplify first, really, if we can. So here are the steps, along with some solutions to this a and b here on the side. So you want to factor everything first, okay? Factor the top, factor the bottom, and that's especially prevalent here in B where you really need to do that. You see how I've done this? I factor the top and the bottom for each. Show as a multiplication. So if we have division, which we're going to talk about later, we want to flip that and multiply. Show as a multiplication. Then we're going to note restrictions. It's really important here, again, at this point to note restrictions. Not at the end, at this point, because we're going to divide out some factors and we might miss a restricted value. And so when we do that, we take a look right here for this a. That pi, remember, is a constant. That's not a variable. R cannot equal 0, and D cannot equal positive 2, because that would make this 0. Over here, I have to take a look at the R's in here and the Y here. And so over here we see that R cannot be 0 or plus or minus 1 when I factored. See how I factored this? It's easy to see. Can't be 0, can't be plus or minus 1, Y can't be negative 3. Follow through now with everything that we did before in the previous example, dividing out common factors. Whatever you have left is your simplified answer. State your restrictions. There you go. What happens if it's division? Well, if it's division, this is really important right here. We're going to factor and we're going to show as multiplication. So that way we can divide out common factors from the top and bottom like we like to do. So remember, if we're dividing by a fraction, we flip and multiply. That's a rule for working with any fractions. Here, this is the tricky part though, no restrictions. Remember, you can't divide by 0. So any values that make this part 0 are restricted. Any values that make this part 0 are restricted. But since we're dividing, we also have to consider any x values that make this 0 as well, because this being 0 would make this whole thing 0, then we'd be dividing by 0. So, long story short, if you're dividing, okay, you have to find restrictions in this part, and this part, and the top over here if you're dividing, okay? So I've got that on the screen. Everything's on the screen. You can pause and look at this if you want, but that's what you do when you divide. 6.3, we started talking here at 6.3 about adding and subtracting. And when you add and subtract fractions, you remember you have to have a common denominator. So here I have an x minus 3 and an x plus 3. Over here, I do not have an x plus 3, so I multiply top and bottom by x plus 3. Over here, this one, sorry, the left side, I do not have a second x minus 3, so that's what I need to multiply top and bottom, so that we have down here a common denominator. Once you've expanded all this right here, then you can gather like terms, and this is your final solution now. You've got one term, and again, you do not have to multiply out the factors in the denominator, but you can show them as combined factors. So this is the answer to this one right here. Okay? So again, you may have to go back and look at that. Again, there's a whole lesson on these. These get a little bit tricky, especially with the subtractions. I'm doing the same thing, except right here that I've highlighted in blue. When you subtract a long polynomial, you have to remember to change all of the signs, right? You subtract each term, which changes all the signs. Everything else turns out to be the same. Note your restrictions, and you're good to go. 6.4, solving rational equations. Okay, when we solve rational equations, in this case, you do not have to get a common denominator with everything. You don't. You can, but you don't have to. What you want to do is eliminate all of the denominators. You eliminate them all by multiplying. I'm going to multiply everything by this. I'm going to multiply everything by this. And I'm going to multiply everything by this. And then you say, wait a minute, this right here is actually made up of each of these. So if you multiply everything by x plus 2 times x minus 3, you are going to then eliminate all of the denominators. Don't believe me? Check it out. If I multiply these two times the first term, the x plus 2, it cancels out with this x plus 2, so it's gone. I'm left with 3x times x minus 3, which I've shown right here. You do the same process. You start over. Of course, this isn't gone for good. It's just, we're multiplying this again by the second term. Well, the x minus 3's are gone. See? And here, both of these terms on the bottom are gone, and so we just have negative 25. So my suggestion for this is just to get rid of the denominators by multiplying by really the lowest common multiple, the LCM, the lowest common multiple of everything you see in each of the denominators. So that's this question. Now, again, check your answers, please, because notice 3 is a restriction, and algebraically, I get 3 as a possible solution. You would have to say, hey, that's a restriction. I cannot have that. And so you would then reject it and just have one answer instead of the 2 that you get algebraically. That is the end of chapter 6, guys. We're moving on pretty quick. My voice is starting to go. I've never done this. This is my first video of this type, doing a whole course in one video, so bear with me. My voice starts to crack. Know that I'm just trying to help you out here, so I'm drinking my water when I can. Okay, chapter 7, absolute value. Absolute value can be tricky, but I'm going to try and make it not tricky. How about that? Absolute value. If you have absolute value of A, let's say, of anything in there, really what that means is that if A is positive, then great, it's the same as A. If this A is negative, what you do is you take the negative version of it. Okay, so it's like the positive or negative version of it. It basically means if you have something like a positive number down here, the absolute value is itself, it's the same. If you have a negative value inside the absolute value, it automatically changes to positive or no sign, if you want to think of it that way. So remember, when you apply the absolute value signs, you're actually just eliminating the negative part. Whatever's inside there has to become positive when you apply those absolute value signs. So look over here. This one is 3 times this. Well, this is negative 5. Nope. No, it isn't. It's actually positive 5 when I apply the absolute value signs. It's as simple as that. Take a look at these examples. Pause it here if you need to. That's how you do evaluate those. 7.2. What about absolute value functions? Well, these are a bit tricky, but again, not really. Absolute value function of, let's say, y equals absolute value of x. No problem. What is y equals x, just x? Well, it's this line right here, okay? I know that I can't have any negative values, so what do? You turn all the negative values up into positive values. And so you get this little graph that has a funny shape. It's like a shape of a V, like that. So wherever the values are negative, negative values, you have to make those positive. So they literally flip about the x-axis there, and they come up here. And that happens with anything. Whenever you see a function, and I'm going to skip down here. Oh, maybe, yeah. Look at this crazy function. This was actually a parabola. And look at this part that was normally down here. Not so much. If it's absolute value, that is gone. It has to flip up to become positive. That's as simple as it is, right there. Whatever's negative has to become positive. Oh, let me go back. I went too far ahead on you. Okay, domain and range. Well, domain is any x values, because it doesn't matter. X can be anything. But the range now, because it can't be negative here, the range for this case, y is greater than or equal to 0. It doesn't go down here anymore. It's not allowed, because the whole thing is in the absolute value signs. The piecewise function simply says that really any absolute value can be looked at in terms of a positive and negative version of itself. And I'll show you that soon when we get to the algebraic part here. Whoa, did I miss 7.2? No, that is 7.2. 7.3, absolute value equations. Okay, if we have an equation containing an absolute value, no problem. One of the things you can do is solve it graphically. And what we do there is do y equals the left side, plot that, which is this blue line, and then y equals the right side, which, no problem, that's y equals 7. That's the red line down here. And of course, when we're solving anything graphically, wherever the graphs intersect, those x values, because remember, we're looking for x, we don't care about the y, the x values, right here, 10 in this case looks like -4, right here in the point, and right here, okay? Those are the solutions to this problem. Hey, cool, hey? Just graph them both and find the intersection points. You may have to look to see how to use your graphing calculator to find intersection points if you need to do that. You can look that up, graphing calculator tips, or in the lessons if you need to know how to do that. I'm not going to go over that right now. Algebraically, okay, here's algebraically. I'm going to leave it on this slide for a few moments as I talk. Again, what I said was the piecewise aspect of absolute value means that this really, you have to consider the positive version of what's inside there, which I have, same, x minus 3, x minus 3. You also have to consider that this could be negative, right? It's absolute value. So what about the negative part underneath here? And you have to consider that too. So really you're solving two separate equations, one with the positive version, one with the negative version. And so here I get x equals 10 when I use this, and here I get x equals -4 when I use the negative version of what's underneath here. And that's where you start. Okay, these are two possible solutions. Please always check your answers. One of the ways the textbook helps you to do this is to identify the domain that's possible or whatever. I don't normally do that. Just say positive version, negative version, and then check your answers. If you always check your answers, you'll never go wrong. If the answers that you get work, so for example, I put 10 in here, if that works, 7 equals 7, great. That's an actual answer. If -4 works and you get, hey, check it out, 7 equals 7, that's great. It's an actual answer. These are your two solutions, and we've checked that, okay? So 10 or -4 would make this equation true. All right, a more difficult one here, I'll let this up on the screen. If you have something that's a quadratic, let's say, the same thing holds true. Take case 1 where it's the positive version of itself, and you'll get a quadratic, use the quadratic formula, and solve. You might have two different x values here. That's no problem. You want to check that both of them actually hold true, that both of them are actually okay. So again, a bit of a tricky one. Put that into the original equation. See if the left side equals the right side. Here it does. Take the other option, the minus, the 1 minus 1, check it out and see if the left side equals the right side. Case 2 is where you use the negative version of that. Again, you get a quadratic, you solve, you have x equals 1, you check it, left side and right side agree in this equation, so you have now 3 answers. X equals or 1, x equals 1, and x equals this one and this one. So you have 3 possible solutions. And we can confirm that graphically. So this is what that quadratic absolute value looks like, as I mentioned before. And here is y equals 1. And so you see that it intersects 3 times, so there are 3 x values that are solutions. And here they are listed up here. Okay? That's solving, that's a big one, but that's solving absolute value equations. All right? What else do we have? 7.4, finally, reciprocal. Okay, reciprocals can be tricky, and so I'm going to go over this just take a little bit more time with this one maybe. But if you have a a function f of x, like I've shown here, just this line. What you're looking for is what is the graph of y equals 1 over f of x. That's what the reciprocal means. 1 over y is another way to think about it. So take all of your y values, and you would take the reciprocal of them and plot that. Okay? So you might have an asymptote, either a horizontal or a vertical asymptote. And so let me just, okay, I guess I need to go over here. Things to check. I thought I had something else on here. All right. The things you want to check when you do reciprocals, let me just give me a second. All right, no worries, no worries. I do have it. It's just down here. So I'm going to take a look at this one. What happens if we have a quadratic? Okay. So here's what you want to do. This is the first thing that I check for is the zeros. So where's the zeros? Right here and right here. What's the reciprocal of 0, 1 over 0? Bad news, right? Can't do that. That is called, that's undefined. So what you want to do is write sketch a vertical asymptote on each of those values. Okay, vertical asymptote. That's the first thing I do. Next thing I do is find out where y equals 1, because this is what it's called an invariant point. Wherever y equals 1, that point on the graph will not change, will not ever change, because 1 over 1 is still 1. Then what you want to do is this, and this is going to be easier to show you on the straight line, I guess, but wherever the function approaches infinity, gets really large out of bound or really small out of bound, then the reciprocal approaches 0. Let me explain. Look at this up here. So here's my 0, that's an asymptote. Here's my y equals 1 right here, and here's my y equals -1. Those are invariant points. So look at the graph here goes up to infinity. Guess what? The reciprocal of a large number is going to be a very small number, and you could actually calculate what these values are. But as this gets larger, this approaches 0. And so this is what this branch of the reciprocal looks like. Conversely, as the graph, or as the function approaches 0, see the y values are getting closer to 0, the reciprocals approach infinity, and so they go up like this. But they never cross the asymptote, okay? So, long story short, this is what your reciprocal function kind of looks like. Oh, I know, this is weird, eh? But this is a review, so you know how to do this already. Okay, what about the parabola? Same thing. As the graph gets large without bound, the reciprocal gets really small, so it kind of goes down like this. And over here too, there's another piece, and so there's the reciprocal. Now, as this blue graph approaches 0, the red graph approaches infinity, and it's really tight there. I know it's not the best graph, but so it kind of comes up like this and goes up towards the asymptote. And what about down here? Well, wherever we have a -1, which is right here, oops, right there, and right there, those are invariant points. Okay, so this approaches 0, so this approaches -infinity, this approaches 0, approaches infinity. This one here, this y value is -4, and this is as low as it goes for the original function. So what's 1 over -4? 1/4. So guess what? That's where this point is. What's 1 over 3? A third. What's 1 over 2? Half. So on. And so this is what you end up having. Something, oops, looks something like this. The graph kind of goes like this. Okay, that's really messy, sorry. But that's kind of what you have. And again, so I would check these 3 things, and that's will help you how to plot that. Okay, all right, boy, this is a real marathon, isn't it? Okay, let's see if we can get this going here. So chapter 9, no, chapter 8. Don't want to miss chapter 8. Boy, there's a lot of gold in there. Chapter 8 talks about systems of equations and inequalities. Okay, so systems of equations. All right, we could have any kinds of equations: straight lines, two linear. We could have quadratic, linear, quadratic. And a system is basically 2 or more of these equations that are plotted or that are considered at the same time. And so there's possible solutions that we could have here between a quadratic and a linear. We could have no solution where they do not intersect at all. And remember, the solutions to any system is where the graphs intersect. So we could have 0 solutions, no solutions. We could have 1 solution where the graphs just touch at one point, or we could have 2. For quadratics, we could also have 0, we could have 1, or we could have 2. Those are all the possible solutions. Solving systems algebraically, okay, it's easy to solve graphically, right? We're not going to talk too much about that. You just plot them and find the intersection points. But solving algebraically looks like this. Okay, you could use something called substitution. This is a straight line and this is a parabola. You could use substitution. So what I've done here for this example is I've taken this first equation, I've isolated for x. See how it's easy to get by itself. We'll just take this over there. Isolated for x. Now x equals this in this system. And so what I've done is I've inputted this into the x in the second equation to make one equation here. That's great. One equation, one variable. Now you go ahead and expand, gather like terms, and you're going to get, in this case, you're going to get a quadratic form. Now this looks funny because it's got a y in it, but it's still a quadratic. You need to solve for that y. You can use the quadratic formula for that if you want. You can try and factor it, but this looks pretty ugly, so quadratic formula is the way to go. And here we go. In this one, we get two possible answers. And I think in this question right here, we were looking for integers. Find two integers such that these equations are both true. And so what you get is, one of them is 17. And so to find the other one, you simply go ahead and plug 17 in for y into one of the original equations and solve for the x. So that's how you get the pair of 12 and 17. That's using something called substitution. Elimination, what you want to remember is that you want to multiply one or both of the equations by a number or two different numbers such that when you add up the equations, you eliminate one of the terms. So here I want to eliminate the y term altogether. So I have 2x squared plus 3x, and then I have plus 6y minus 6y. Those are gone. The y is gone. That's a way you can eliminate one of the variables, and then you carry on from there. It's a quadratic solve, and you can carry on. So that's elimination. You want to eliminate one of the variables. And that's it for chapter 8. That was really quick. That's 8.1 and 8.2, short chapter. Finally, let's burn through number 9. We're almost done this massive review. Where are we at here for time? Oh my goodness, 51 minutes. This is going to be an hour. My gosh. Well, I love you guys, and I hope you guys are learning something. Again, if you have me on fast speed, I apologize. But you're going to get this done in 30, 40 minutes, and you're going to be studying for your final, and it's going to be awesome. So let's do 9.1 real quick. I'm getting tired. I got to go home too. So 9.1, linear quadratic inequalities. Now, chances are you've just got finished doing this. This is probably the freshest in your mind, so I'm going to go quick with this one. But solution region. Okay, so if we have an inequality with two variables, like this, then what you're going to be finding is a region. Now, you're going to be finding x and y pairs, right? X and y. And those pairs manifest in the form of points. And so a solution region will have points, a collection of a billion trillion points that constitute the answers to, or the solutions to this inequality. And so when you have two variables, you're looking for a solution region. Okay? One of the things you could do is you could test the inequality with a test point. You could pick a point that's either above or below what we call a boundary line and see if the inequality is true. And then you know if that point is one of the such points that's in the solution region. Okay, let's talk about the boundary real quick. The boundary line, that is what the equation of the corresponding inequality would be. So if you write your inequality and exchange this for an equation, then you're going to get the boundary line. If the boundary line does not have an or equal to, that's when you stay away from the solid line and you put a dotted line, as I've written down here. So if the inequality has an or equal to, we have a solid line as a boundary. But if it does not have an or equal to, we have a dashed line, meaning that the solution region goes up to, but not including this line. They are not included in the solution region. So you probably just remember just learning about this. 9.2. Okay, in this case, we only have x showing up in the inequality. That's important. That's a different way of solving. What we need to do is we probably should still consider what the equation is, right? Because we do want to find out where the sections of the x values, there's three important sections usually with these parabolas. So if you plot the parabola, what you're going to find is that there are going to be a certain x value or values that will cause this equation, this parabola, to equal 0. Those are the x-intercepts, okay? Those are the solutions if it's an or equal to. Now, in yellow up here, I have the branch or the part of the parabola that is positive. You see how this is above the x-axis. This is where all the positive y values are. So if we were looking for this one right here, we're looking for all of the x values that cause this expression here to be positive. You see, that's positive, greater than 0. Well, this is where they're positive. So my solutions are the x values that correspond to this positive part of the parabola. So anything greater than, and there's no equal to here, so anything greater than 4, see, would be part of the solution for this inequality. Also, there's a yellow part of the graph over here, so anything less than -1 is also a part of this particular inequality. The other part is where the parabola hangs below the x-axis. Well, these are negative values of the y. See, all these values are negative. And so we want the x values that correspond to this part of the parabola. And that's where we write something like this. X is between -1 and 4. All right? So in one variable, you're just looking for the one variable that you're looking for. And that's just a part of what's going to be the x-axis. Another way to do this is to use roots and test points. So if you have a parabola, let's say this is your inequality right here that you're trying to solve for, find out what the roots of the corresponding equation are. So factor it, find the roots. These roots mean that on the number line, right, -1 and 3, those are going to be the points where the parabola crosses the x-axis. And so that's going to split the number line or the domain into 3 parts. And this part over here has where x is less than -1, this is between -1 and 3, this is beyond 3. And what you can do for this, now that you have the roots, you pick a point, an x value that's in each of the regions, and these are the ones that I've chosen, and I've shown you down here, and you simply test that x value with the inequality that's given. If the inequality turns out to be true, where this one is not true, so this is right here, this is not part of the solution region. If it turns out to be true, like x equals 1, that makes an equality that's true. So that means that anything inside this section right here, I should do that in a different color, this section, those are good. That is yes. That's my solution region, because over here is a no as well. Okay? So again, pick a test point that's somewhere on the number line and find out if it makes the inequality true. If it does, that's the section that has all of the solutions to this inequality. All right? And finally, not finally, but sign analysis. Sign analysis is something special. This is different than a test point. What you want to do is you want to take your quadratic, or whatever this is, and factor it. Okay? Once you have the two factors, what you're going to do is you're going to list these two factors on the side of this little chart here, and then what you're going to do is determine where on the number line, which would be represented by this horizontal line, where in the number line it's 0, positive, and negative for each factor. So you want to analyze the signs of each factor. So x minus 3 is 0 at x equals positive 3. That's 0, so I put a 0 above positive 3, which I place on this bottom number line. Now, any values less than 3 cause this factor to be negative. You see that? Like a -5 or a 0, it makes this whole thing negative. Anything beyond 3 makes it positive. There I'm analyzing the sign of this factor. I want to do the same thing over here. -1 is 0 there, minus there, plus there. The function now, look at, remember we're multiplying. So what's a negative number times a negative number? Well, that's positive. So that function is actually positive in this region. A negative times a positive is negative, so the function is negative there, and positive times positive there. Remember too that this is 0 here, and remember too this is 0 here. So now you have analyzed each factor, and you're able to determine the sign, or the positive or negative or 0 nature of the function. So now I look at this part right here, and I can find my solution set. So I'm looking for x values that make this negative or less than or equal to 0, and that's everything between -1 and 3. So -1 less than or equal to x less than or equal to 3. That's how you write everything between and including -1 and 3. So that's sign analysis. Okay, finally, this is the last section. Last bit here. I'm going to make it under an hour here, I'm pretty sure. So 9.3. 9.3, we're talking about inequalities here, quadratic inequalities. Now, I just put this one up here. This is linear for sure, but we're able to, if you're given a graph, you can create the inequality as well. Note the slope of the line. Note the y-intercept. Here's the slope, y-intercept. And a little hint is if you have y positive and by itself, and you have a less than, and you have two variables, you can shade the region that is below that line. Okay? So less than means shade the region under the graph. Greater than, if this was a greater than, then you can shade the region above the graph. Just a reminder about the boundary lines. This is solid if it's or equal to, and dashed if it's not or equal to. All right, so finally, let's take a look at this quadratic. Y is by itself, it's positive. We have a less than. That means that everything underneath this graph is probably going to be a solution, and that is the case. So shade underneath that graph. Always a good idea to check with a test point, and a test point I like to use is 0, 0. That always is easy to find out, But you may get confused on the test if you always check 0, 0, because 0, 0 sometimes is part of the solution set and sometimes is not. So I would encourage you to pick a point that you think is in the solution set. In this case, this point would be 5, 0 here. You see that? 5, 0. And so what I'm going to do is I'm going to plug that into my inequality. I'm going to check this with a test point, plug it into the inequality 5, 0, and this happens to be true. So my check or my verification is true. Okay? All right. We're almost done. What if you're given an equation like this or a question like this on the test and you're asked to determine the inequality? No problem.